Hey! How's it going, everyone? Alright, I'm sorry for being a little bit late today. Just had some stuff this morning, so just a little bit busy. That's okay, time for some Haskell. We're gonna keep going on with the FP course. How's it going, Vegardno? How's it going? Hey, Subroutine, how's it going? Alright, let me just get up where we were with the FP course. Where were we? So I'm guessing we got through applicative from the looks of it. Hard G, alright. I'm not a lecturer, I do teach Haskell at work though. I work for a company called Atlassian. I work on this product specifically. Here we go. Atlassian Marketplace is the product I work on, and I work for this company, Atlassian. And so I teach functional programming for Atlassian. While working on Marketplace, like a lot of Marketplace is written in something called Scala, and we use a lot of functional programming. And so I teach functional programming at Atlassian, trying to get the Marketplace team, trying to get people better at functional programming for the Marketplace team, just because we use so much functional programming. I mean, I don't only teach, it's just that's something that I also do at work. I spend probably, I don't know, 10% of my time teaching. So we got through funct and we got through applicative. Finished list. Did we finish off applicative? Did we actually finish it? It looks like we finished duplicative, so I guess we're up to monad. I think that's what we got up to, did we? Let's open this up, any max. Yeah, I think we got through it. We did filtering, so I think we got through this. So I guess we're up to monad now. So I never remember where I ever get up to with these courses. I've got at the moment I've got 2 classes doing the FP course at work, and so they're at different places in it as well. So I always forget where I'm at just because I do it so much. Oh, okay, you got go ahead to introduce Scala. Oh, interesting. And you'll be teaching it too. Oh, awesome, cool. Cool, so let's go to monad. Okay, so before what we saw was applicative has pure and this apply thing. This thing is pronounced apply. We pronounce it apply. Or at least I pronounce it apply. I don't know, do they give it a different name here? No. Sometimes how I pronounce things is slightly different from what the FP course, how the FP course says to pronounce things. So I pronounce this one apply. They don't really have anything here, so I'm gonna keep calling this one apply. This one, when we go up to monad, notice that so when we say that something's a monad, it also has to be an applicative. So remember, this is the superclass constraint. So we're saying that for something to be a monad, it also has to, or already has to be an applicative. It has to be an applicative as well as being a monad. And to be a monad, we have this thing, which is pronounced bind. And this thing here is pronounced bind. This equals less than is pronounced bind. This is slightly different from in the standard library. The standard library in Haskell has something that looks like that, so it's just like this is just kind of like a backwards version of this. And in the standard library, we usually pronounce this one bind, but in our FP course, we're going to pronounce this one bind, just because it's more consistent. So if you flip between these two, notice how I'm flipping between them. Notice how FA to FB, FA to FB. That's the interesting thing, right? So when you have, we had this thing called Fmap, right? So Fmap has the type A to, if you give it a function A to B, then you get back an f of A to f of B. And then we had apply, which was this thing, the spaceship operator, which is f of a to b. So if you look at these, you might notice a little pattern. Now we're going to write this one bind, which is slightly different. So if you look at this, you'll see that what we've done is written kind of different types of functors basically. So this one's called a covariant functor. So the original functor that we wrote, more specifically this functor, it doesn't say it in the name, but it just says this functor. But this is actually pronounced like, this is actually technically this is called a covariant functor. So that's what we've got. This is covariant functor, and this is what we call an applicative functor. And the interesting thing is we're going f of a to f of b. And then we call this one a monad. Some people will call it a monadic functor. And so it goes from a to f of b, and we get back f of a to f of b. And so that's the interesting thing. And notice the similarity here. We're given something, you get back a function that goes from f of a to f of b. And that's kind of like the general idea of a functor. And so you got things that are like, you got a covariant functor, but you've also got a contravariant functor, invariant functor, exponential functor. So you got all these different types of functors, and that's what we're defining. So monad, applicative, and functor are all different, just different types of functors, just different, given different input, you get back a function goes from f of a to f of b. So that's the interesting thing. These ones actually form a hierarchy. So you got fmap, and then you got apply, and then you got bind, and they kind of form a hierarchy. Fmap is kind of like the most general thing. It's the thing that works on most things, but you can derive the least functions from it. And with apply, it kind of steps up a little bit. You can derive more things, and it applies to less things. It applies to less data types than what fmap does. And monad goes a little bit further. There's certain things that you can apply with, but there's not that you can't bind with. But bind lets you derive a lot of useful functions. And so when people talk about monad, really what we're talking about is the kind of like the extra things that we can get from knowing that something is a monad. We can derive a lot of useful functions, and so that's the interesting thing about monad. It's not any more interesting in terms of types than functor. It's just the implications of monad are a little bit more interesting because we can just derive a lot of useful functions from monad. But there's nothing special about it. It's just something that gives us a lot of useful functions. There's nothing really special about it. It's still just a way of going f of a to f of b. So monad is not very special. It's not very. It's just something useful. That's all. So exponential, yeah, exponential is a good one. I don't know if there's a good symbol for it, but we sometimes call it invariant map. So exponential is the kind of the mathematical or the algebraic version of an invariant. So they're the same thing. Invariant functors, they're the same thing. Yeah, it looks like invariant. It's exactly invariant, which is just a to b, and then well, we can do it this way: b to a, f of b. Yeah, it's exactly invariant. So invariant functor is something that's covariant and contravariant, but you don't have to know anything about that. Let's keep it basic. There's the point is that there's just a lot of different functors. These are the ones that we're going to be showing right now, but there's more, and monad is just a useful one that we're going to be showing. Okay, so this one's called bind, and what's changed here is that we've gone, instead of having an f of a to b, we now have just a function a to f of b. And that's all it is. We're just changing where the f and the a, well, I guess the f and where the f is. So before with applicative we had this, and now we've got that. So we're just kind of moving this f inside of this function. So now to get an f, you have to give it an a. Alright, so we're going to go through and implement the applicative operator using the monad. So we have to use bind to implement our apply operator. So this is just kind of like another version of the apply operator, and what we're going to do is try and implement. We're going to show that that anything that's a monad, we can derive the apply operator. So given this thing, we can derive this thing, is the point. Given this, given bind, we can derive apply. And that's what we're going to show. Alright, so this is f of a to b, and this is f of a. And we are going to implement, what's the whole say? Whoops, I should open up this in tmarks. Alright. What about f of a to b? And yeah, well, you have just derived something. You've just derived, what's the symbol for that? I can't remember the symbol for it actually. Is it, well, you've derived, cobind. Which we usually call extend. That's it, extend we call it. I can't remember the symbol for it, but it's called extend. And this is what you've just derived is called a comonad. So yes, that exists and it's a useful thing and it's called a comonad. It doesn't come up as much as monad does. Monad comes up everywhere. But yeah, comonad is the thing, and so it is used, not a huge amount, not anywhere near as much as monad, but it is a useful thing to come up with. Comonad is a useful data type, useful type class, I should say. But yeah, if you just move these, if you just move the f around, or you kind of give it different, if you give something here, if you just kind of put in like your own input to this function, and if you just keep it consistent here, f of a to f of b, you can come up with new different type of functions that people haven't really talked about before. Like I've been looking into, so there's what I was talking about before was like the exponential and the invariant functors. But what if you gave it an isomorphism a to b? Or what if one side was not an isomorphism, but it was kind of like what they call an epimorphism or a split monomorphism? And there's kind of different things you can do here. Like you can basically change this function around to be like, how about something like that? And what type of functor is this? I don't know. You can come up with things like that. And so what you just came up with is called a comonad. And people have already done that one. That one's a good one. Okay, so we have to implement an f of b from these things here, what we have in scope, f of a and an f of a to b. So what can we do on this? We need to use bind. So what should we bind? We'll bind, it doesn't matter which one first, I think. Actually it does, doesn't it? We need to bind in the order. So I'm just gonna chuck in a hole there. So now we have to go back in f of b, yep. And what we have now in scope though, is we got this in scope. I'll just introduce this in scope. So we've got a function a to b, and we have an f of a. Does anyone remember what we can do with that? There we go, so that's how to derive apply. I'm just going to refactor slightly, because remember that if you see something that's what would you say? So if you see something like this, if you've got something infixed, you can just drop it. You can just drop it like that. You can also do it. It gets a bit tricky. But there we go. So the idea is that to derive the so I mean I just used types to get there. Hey, how's it going, volts? So I just used types to get to the solution. Bind on this one, and then I had this thing in scope, so I just fmapped it. It's really just directed by types to be able to derive this, to derive apply. So this is apply based on just based on bind. So we're not implementing. So we're not. Oh, how's it going, Sage? Thanks for the tab. So we can implement apply based on bind is the point. We only need bind and we need fmap, and we can implement bind. So that's just to show that yeah, exactly. Type holes are really good for deriving implementations. It's really straightforward. So that one, like, sometimes it feels like you're kind of not learning if you're just going through the type direction stuff, but I think it's good. Like a couple people I've worked have said, well, I don't really feel like I'm learning anything because I'm just, you know, using types to get to the implementation. But I think that's fine. I think it kind of, as long as you kind of look at all the possibilities, like how can I implement bind? How many possibilities are there? And there's a couple of possibilities to implement this. And if you take that into consideration, if you're not just blindly just choosing a random thing, and you're actually like kind of considering what the options are and how it's kind of connecting together, I think that's still a useful thing to do. Alright, so that is apply in terms of bind. It's just to show that that if you have a monad and you have this bind thing, bind is powerful enough to implement a part of the applicative. You also need fmap as well. So you need bind and fmap, and that's enough to implement the applicative function, the applicative apply. And that's all that's to show. You just using bind and fmap, you can implement the apply operation. Or you can derive it. Alright, so we're going to actually implement a monad now. So we're going to implement a monad for exactly1. If you remember exactly1, remember info is really good. So info exactly1. I don't know anything about exactly1, so let me type in info. Here we go. It tells me that exactly1 is a data type that takes another type, and then well, exactly1 is a type constructor that takes a type, and also it's a data constructor that takes a value of that type. So we could say exactly1 of true. Get the type of that. So exactly1 of true is exactly1 of bool. Alright, so we know something about exactly1 now. So we've got this function, and we have an exactly1. So here we're doing pattern matching to extract out the value. Actually, I'm gonna not do that. So this is gonna be exactly1 of A. What do we have in the scope now? So we need to return an exactly1 of B, and what we have in scope is an exactly1 of A and a function A to exactly1 of B. So if we browse where our exactly1 type is, then we've got this thing in here. Here we go, we've got run exactly1. So we could say so instead of pattern matching, you can use like what we call fold functions. This is kind of like a fold function. So it's just a way of getting the A out. So now we've got the A here. So we've got this value A, which is type A. So it's just unwrapped the exactly1. Think of exactly1 as just a wrapper around a value, and we just run it. So we get out the A. So now we've got an A, and we have a function f A to exactly1b. If you look at what we need to return, exactly1b. Combine that together, and you see that the implementation would just look like f of A, and that compiles. And if we have it like this, remember that there's a rule that if you see the thing on the left hand side is the same as the right hand side, you can drop it and replace it with composition. So there we go. So that's an implementation. But if you noticed anything, if you had a good eye, you might have noticed this thing. Bind exactly1, which is exactly the type of that. Bind exactly1 looks exactly like that. So what we could do is drop that and replace it with bind exactly1. So there we go. You can just say that it's equal to that. Bind is equal to bind exactly1 for this case, for the monad for exactly1. Alright, so list. So we've got a list of A's, function A to list of B's, and we need to return a list of B's. I'm going to, what's the best way to do this? There is, if you look in here, there is a, I'm gonna go through this quickly. You can see here there's something called Flatmap, and Flatmap is bind. So if you're used to Scala calls it Flatmap. In Haskell we call it bind. But it's Flatmap, bind, they're the same thing. Is there another name for it? Does anyone know a different name for Flatmap or bind and something some other people might be able to be familiar with? I know Flatmap, bind. Is there one in C#? Link has got something like this, doesn't it? Select many, is it? So the implementation is just Flatmap for list. That was straightforward. And optional, if you look at this, we have an optional of A to optional B, and then optional B. If you look into optional, it should be somewhere. Bind optional, there is bind optional in there. So you just say bind optional. I think we'll actually implement this one because this one should be pretty easy, I think. Or maybe it's not that easy. There's not really a fold operation on this. I'm gonna say that's good enough. It's just a bit tedious. You can derive, it's just a little bit annoying without the fold function. I'm gonna keep going. Here we go. This one, let's do the reader. Reader is actually interesting. In this one, we can't really just derive from an existing implementation. We'll have to actually do this one. So this one, remember, if you looked at the applicative one, so with applicative, what do we do? There you go. So this one, remember, there's a little bit of syntax going on. A little bit of syntax, which is that we're using the arrow as a type constructor. And the way to read this is our functions take a type. So whenever you see star in a kind, so we're talking about kinds, and you don't have to understand too much about it, but just know that when we have when we're asking for the kind and we see a star in a kind, that means type. And so we're saying that function arrows take one type and then another type and give us a type. So what that means is that int to string is a type, or string to int is a type. And what we're doing is saying this one's string, this one's int, and we get back a type, which is the whole thing, which is the function. So this is a type that represents a function. So that's how to read that. And what we're saying is that here we're saying we're only using the first one. So remember how in Haskell we got this currying thing, or we got this thing where all functions only take one argument, and that's the same as types. Types only, when you have type constructors, which is kind of like functions at the type level, when you have type constructors, they only take one type. So when we read this, and remember, this is also prefix notation going on. So usually when we write things, we write them, when we usually use operators, we write them infix, but we can also remember that we can also write them like that. So this is called infix, and this is called prefix. So these are the same things, they mean the same thing. And usually when we write functions, we usually say, well, when we write the type of a function, we write it like that. But it is possible to write it exactly like that. These are the same thing as well. So this is the same thing as down here. Infix and prefix. And what we're saying here is we're saying we are constructing, we're using int as the first type, and then we're saying give us so then we get back this. So it's just like if we say times 2. So that says that we've applied the first argument to times, and so then it takes one more. So we can say so we've applied the first argument, and then we're applying the second one, and we get back a value. And it's just the same with types. So here we're saying apply the first type. So this is a function that takes an int and gives us back something. That's what that means. We haven't specified exactly what it returns back yet, but when it takes an int, we know that. So when we are writing this instance, we're saying it takes a t. That's all we know about this function. It takes a t, and we get to specify later on exactly what it returns. And so in this case, this is a function t that returns b. This is a function t that returns a. This is a function t that returns b. Hopefully that makes a little bit of sense. And so we can actually rewrite this away from prefix notation because people are probably more familiar with that. So that is equivalent. And also remember that this is the way that that functions associate, the function type associates. So we've got a to t to b. That's the same as that. A, t, b. It's exactly the same thing. Alright, so it's all compiling, and so none of that syntax, none of the stuff I just changed, which is just syntax. None of that actually changed the semantics about anything. Okay, so what we have in scope now is a function f. Oh, but if you might also notice that this is the same thing as well. If you see parentheses on the right hand side of a function, you can actually get rid of it. So that's the same thing as well, and so that actually like helps us out with the implementation a little bit. I'm going to keep it there for 1 second. We're going to say f, what's this, atb, oh, atb, and ta, and then this, we're going to return, let me put in a whole to do, we're going to return a function t to b. So we could, the constructor for functions is lambdas, so we could have this, we could write it like that. So we've got a t in scope now, so I just asked myself, how do I construct one of these? And then I started constructing it. So now I've got a t in scope. I can do things with that. But another way of writing this is because we know it looks like that, we can actually write it like this. That's the same thing. So we got rid of the parentheses here. We didn't even have to do that. We really don't have to do that. That's the same thing as well. That compiles. But we can drop that, and it just becomes a little bit more obvious that it looks like that. Got a function, another function, a t, and we have to return a b. Just a slightly different way of writing it, and just might make it a little bit more obvious what we're doing. Alright, okay, so we've got this t in scope, we've got this function t to a, then we've got this atb, and we need to return a b. So how do we get a b? If you look at everything in scope, how can we get a b? The only thing that mentions b is this thing. Okay, so this thing needs an a and a t. How do we get an a? This is the only other thing that mentions an a, so it has to be this thing. And then it also needs a t, so how do we get a t? Well, we've got a t. So that describes the implementation right there. If you just, because it's so there's so much polymorphism going on, there's a, t, and b. We know nothing about a, we know nothing about t, we know nothing about b, we know absolutely nothing. All we know is that we have functions in scope that do things with those, but we don't know anything about it. We don't know if a is an int, we don't know if b is a boolean, we know nothing. So there's nothing other than being able to, there's nothing we can do with them other than pass them around. That's the rule with something called parametricity. The idea is called parametricity, and it means that polymorphic types have limited capabilities. And limited capabilities means that it kind of directs you towards an implementation. We use this thing called parametricity to kind of direct us to implementations of functions. So because A, T, and B are all polymorphic, we know nothing about them, there's only a certain thing we can do, and there's actually only one implementation for this. All the implementations are equivalent no matter how you write it. There's only like, if you look at it, there's only like one way to get a T, there's only one way to get an A, and so you have to do it. Okay, so let's have a go. So we know that we're going to use this ATB thing to get a B, so ATB, and then we need an A, and we need a T. So let's put in holes for those, and so now it says A needs to be an A, underscore T needs to be a T. Okay, cool. So here we can fill in that T is T, so we've got a T, so we can fill in that one. Now it says I just need to fill in one more hole, which is A. So we need to get an A. How do we get that? Well, we've got this thing. T, A, go to T. And that's the implementation. So what's interesting in this one is that we're using T more than once. And that's the interesting thing about the reader monad, or the reader type. So the type of functions that look like that. They use T. They use like their variable more than once. And so what's interesting here is that if we run this thing, so we've got 7. And so that'll be 7 plus 10, is it? 7 plus 10, and then multiplied together. So that'll be 7 times the result of 7 plus 10. So that'll be 17 times 7, is that right? 17 times 7 is 119. Cool. Yeah, so that's exactly what it's doing. 7 plus 10, and then goes to 7 times the result of the plus 10. You don't really have to understand how to use it. Just know, just understand kind of like the syntax around this, I guess. Just understand the syntax around what we're doing with functions and how we're reading how we're reading this type. The reader monad is useful for people use it for configuration. Eventually, there's something called reader T, which is a little bit more useful. Reader by itself is not the most useful thing, but when you build up to something called reader T, then what you can do is it does exactly the same thing as this, just with another monad available. So people use reader T for configuration. So if you had a reader T of like my config file and IO, that means you can run things like you can print things to the screen, or you can read things from the command line, or you can do things. That's the IO part. And config means that you've got a configuration in scope, and so you can just as many times as you want, you can read the configuration and do things based on it. And so this config is just a data type, and you can write it yourself. So I could say like we're gonna say like data config. Thank you for the follow. So I can say config has like a name, I don't know, app name. And so then I could write a program based on reader T that keeps going, like I could say like, I think ask is usually, is it ask? Might be ask. Or is that state? I can never remember. Ask, and then I could say print that. I could print the app name. So this is a valid thing. It just says like go off and read the configuration. Or actually this one's even better. We could say asks app name and then print it. So this is what reader is useful for. You can say go off, read the configuration, get out the app name, and then print it out. Hey Ethan, how's it going? So reader is useful for configuration. Basically, that's what it represents, like some sort of configuration. We use it at work a lot, reader. Okay, so now we're going to implement join. So we've got an f of a. What do we have to implement? Return an f of a. What we have in scope is an f of a, and what we also know is that f is a monad. So we must have to use this in some way. Pretty much, I mean, if it's not applicative, if it's monad, we know that we're going to have to use bind in some way then. That's just kind of a hint based on fpcourse. If it's given us monad, we know that we're going to have to use bind in some way. So let's try and use bind. The only thing that we can use bind on is what we have in scope, f of a. So let's see what the hole is now. So I'll just put in a hole in for what we need to bind to. So remember, bind takes a thing. Actually, I'm using the wrong operator. I need to be using this one. Bind. Oh, my space max slows down a lot as well. I'm using something called Dante, which, because I don't use stack doesn't work. So I use something called Dante. And Dante has some support for Nix, but I think it's failed for me. Try Dante instead. If you're using Intero, don't use Intero. It doesn't work. Use Dante. Dante's a little bit better, but it does slow down for me. I think I've got a problem here. Dante, do I have any? No. I had an error come out just before, I think. I don't know. I need to fix Dante. It's not quite right, but it somewhat works. Well, Spacemax isn't that bad for me in general. Anyway, I've put in a hole for bind here, just because I know that I'm going to use bind because I know I've got monad. This is the only thing I can bind on because that's the only thing I know that has a monad. So bind on that, and now I've put in a hole for where the function is. If you look at this, the function needs to be f of a to f of a. What's the function that does that? function that just returns itself, which is the same as ID. So that's already a function built into Haskell, ID. And we can also drop the right hand side. Remember that rule. Drop if it's on the same as the right on the equal sign. If you got the same thing on the very very right of the left hand side of the equal sign, then you can drop it from the right hand side of the right hand side of the equal sign. And just drop the last part from each. Alright, so that is join. So this one is bind but flipped. So we've got a f of a. This is the one I accidentally used just a second ago. We need to give back an f of b, and what we have in scope is an f of a, so implement it like that. But we could also write it like, because all we're doing is changing the arguments. Haskell has a built-in function for that flip. That one was easy. Alright, now this one's going to get tricky. We're going to do Kleisler composition. So we're going to have a monad. And we're going to have two functions, b to f of c, a to f of b, and we're going to compose them together. So remember that compose looks like, what is it? I am using the Vim key bindings. So remember that compose looks like this. And what we have been asked to write is the fishy operator. People at work call this the fish operator. And you might notice the similarities between the compose operation and our Kleisler composition. So these are just two different forms of composition. One is composing but with an F. See how there's an F at the end of each one of these. So it's composing but with an F inside of it. Okay, so let's introduce these things. B, F, C, A, F, B, A. Alright, so we need to give back an f of c, and what we have in scope are these things. So how can we give back an f of c? There's only one way to get an f of c, right? There's only one mention of c, so it must be this. So we must have to use bfc. So let's use bfc, but bfc takes an argument of b, so let's put in that to do. Alright, so we need to give it a b. How do we get a b? We get b from here. So we have to use this AFB. But AFB doesn't give us just a b, it gives us an f of b. So how can we do that? Well, if we use this bind thing. So remember that bind will kind of take the, where are we? Here we go. So if we bind on that, if we bind on the result of this, so we've got an f of b, so bind f of b. Our type of bind is, actually I don't know that in scope. So a to f of b, f of a to f of b. So if we bind, but with, oh, I'm using the reverse bind again. But if we bind with f of b here, then we'll have b to f of something, f of c, and then we get back an f of c. So if we did that, whoops. So now what we have to fill in is an a. Is it? We have to fill in an a? Yep. We have to fill in an a, and we have an a in scope actually, so we can just do that. there we go. So that is, I think that's it. Yeah, that's everything. So now you know everything about monad. So that is, that's composition that we can derive. And it's really just, you know, just taking in an argument and just using the bind operation. Cool. So I can't remember what the next thing is. Are there any questions about monad while I'm trying to find out what to do next? I guess we could do FileIO. Yeah, we can do FileIO. FileIO kind of uses the what's practically useful for Clydesdale? Clydesdale is useful for a couple of things, but if you've ever got it, like, it is possible for you to. I have this every now and then. I have a function where I've got a couple of functions and I just want to compose them together. And at work we have like a kind of like a pipeline where you do something monadically, then you do something else monadically, and then you do something else monadically, and we just use Clydesdale composition. So it's just that if you've got like a big pipeline of different functions that go off and do some sort of I/O or do something in your application, and then you've got something that comes after that, and then something that comes after that, then you can just use this Clydesdale composition. So here, like, you could say I/O, for example, and I don't know, this one could be your raw input. Maybe this is like stage 1. Sometimes we have things like that inside of our application at work. Just something that processes it kind of in stages. Clydesdale is useful for doing that. So you just kind of compose them together and you kind of get new stages. So I could add like a stage 3 on just by adding another compose in there. And then I could add like a stage 3, stage 4, and so on. Yeah, basically like a, well, yeah, a multi-stage rocket launch, that's a good one. So we use it for that at work. Clydesdale, there's actually a data type called Clydesdale as well, which kind of converts this thing into a data type, and then you can use this normal compose operation. And that Clydesdale data type, if you actually look at it, it also is the same as this data type in a way. And so there's kind of like a Clydesdale is kind of this reader T that we wrote up here. So I was showing off reader T, which is a way of reading a configuration but also being able to do something at the same time. So reader T kind of wraps up another monad. And so reader T provides configuration for another monad. So if I've got an I/O, I can have configuration inside my I/O. And reader T is that Clydesdale data type. So if you wrap this thing up into a data type, if you wrap the idea of this into a data type, you could say this F is I/O, and then that represents reader T. So Clydesdale is reader T. So that's something else to think about. Okay, so we're going to implement this thing called FileIO, which is a way of we're going to use everything that we've learned. So we've learned Fmap, applicative, and monad so far, and we're going to use all of those to implement a program, an actual program. So we're actually going to use these things to practically write a program. So something that does these things. It will be able to read from a file, print out to the screen, get the arguments from the program, and we're going to just use applicative, monad, and functor to be able to implement this. That's all we need to know. So now that we've known these really abstract things, we know apply, we know bind, and we know Fmap, we are going to be able to implement real programs just based on those. Okay, so the actual program I'm going to write is given a single argument that is a file name, read that file, and then for each line of that file each line of that file will contain a name of another file. So read that file in and print out the name and the contents of that file. So for example, a.text, b.text, c.text, then it'll just print out, hang on, where is it? Example output, here we go. It'll print out this. And this is how we run it. We use this colon main So that's running it. So at the moment it's just an exception, it just throws, and our goal is to remove the exceptions and actually implement it. Pretty straightforward. So this is just to demonstrate that you can, using all this pure functions that we've written, just all these functions, all we've written is functions so far. And that's actually what we'll ever do, but just using functions we can implement real programs. And so there's no real downside to doing functional programming because we can still write practical programs just using functions. So we know a way of doing that, and so that's what we're going to show. It's just to show that we can still write very useful really useful programs just using functions. There's no downside. Okay, so we're going to use the tips here are really useful. It includes lots of tips. So use getargs and run. So let's use getargs. What is the type of getargs? An IO of a list of characters. And what we know about IO, if we look at info IO, what we know about IO is that there is a functor, applicative, and monad. So we can use all these operations. We can use fmap, apply, bind to implement IO programs. Okay, so we're going to use getargs. So let's say getargs and run. Where is run? Here we go, run. Okay. So let's use getargs. We're going to bind. So if we look at the type of getargs, it returns an IO and a list of characters. So we're going to do something with these list of characters, and that's what we want to do. So we're going to get a list of characters. Actually, it's not a list of characters, it's a list of characters is a list itself. If we look up info, it's a list of list. So we're actually going to get a list of list. So here we go. So now I'm going to put in a hole here. So what I have to do is do something with these list of list, and then return an IO of unit. So remember, this is unit. We implement this for the void. So unit is a type that has one value, which is the unit type, a unit value. So it's just a unit is just it's a type with one value. And that's all it is. Okay. Okay. So we need to return an IO of unit. And it says use run. Tip is to use run. So let's look at run. Run returns IO of unit. So this might match up. So run. Okay, so now we need to get a file path. If we're going to use run, we need to give it a file path. But the thing is, what if x's is empty? Oops. So I'm going to pattern match on our I'm going to pattern match on this list that we get in. So in the case that we that when we call main and we don't give it arguments, main, here we go. So in the case that we call main and we don't give it anything, then that will hit this nil case, right? Because this is the x of x's. So our list of list is the arguments we get in. So that's a list of characters, and then we can have a list of them. So we can have main with no arguments or main with 2 arguments. And so in the case that we have no arguments, I'm going to print out something. How do I print out something? What do we have in scope? Put str line. So I'm going to say that. But in the case that we do get an argument, so here I'm going to say given a head, ignore the tail. Put an underscore here, so I'm going to say ignore the tail. So ignore the tail, and just use the first argument. And that's what that means. Just use if there are other elements, that's nil. If there is an element, then that's something cons. And so just use the first one. So here I should be able to say main, and it should say no arguments. And then if I say something like that, it's going to use the first one, pass it into run, and run throws an exception. Well, this code, so I'm going through something called fpcourse. Fpcourse is I'm going through this thing, Data61 fpcourse. It's a what do you call it? It's like like a workshop that people up in Brisbane run in Australia. So I'm going through this, just showing how I teach it. And this program is going to just go through and dump out a heap of files. That's all it is. It's just a really simple program just to show that we can use pure functions to implement a real program. So this whole course is about functional programming. So we've only implemented pure functions. So functions that only take an input and map it to an output. That's all they do. And I'm just showing that we can use that exact concept to implement a real program. And so all of these, all we've done is implemented pure functions. So this is a pure function here. We know that bind, that's a function. We've implemented a function here. This case is a function, and then this is a function. So all of these are just functions, and all we're just using is this thing, this IO data type. So this is just a data type, and we're just using this IO data type to create a program. So we're just writing pure functions to create a program. That's all that this is showing. So now we've got a file path. We're going to use get files and print files. Get files of our FP. Now let's look at the type of get files. Get files takes a list of file paths to IO. Hang on, do we want get files? Yeah, we do want get files. Okay. Why is it taking a list though? That's interesting. Okay, just a single argument of a file name. Okay, that's fine. So we use get files. And we just need to give it a list, so put that into a list. And what we get back is this thing here, so we get back a list of file path and characters. So now we get files. So here we go. Found hold to do, IO. We have a file, we have this thing in scope. It says to use print files. Where's print files? Here we go, print files. So that lines up here. What we have in scope is this, and that's an argument here, and we need to return IO. So we should be able to just chuck in print files. Whoops, there we go. And remember, if you see a lambda, you can just drop it like that. So there we go, we're getting close. And now we're gonna have to implement get files, get file, print files, and print file. Alright. Where should we start? Let's do get files. Let's try and run it as well. We'll just get another exception. Yep, cool. Okay, so now we have to implement, let's implement get files. So given a list of file path, give us back that, an IO of list. So we need to use this get file. Okay, so we need to use, so we've got this list. Someone might remember that we implemented a function in, we implemented a function somewhere else that's useful. So let's go here anyway. So we need to give, so we've got this list of file paths, and we need to give back an IO of list of this thing. And so if you look at get file, we know we need to use get file because the hint tells us to use get file. So if we look at get file here, file path to IO file path to characters. So notice how this is similar, but we've got this list thing involved. So we actually got, instead of a file path, we've got a list of file path. And then we have this thing here, IO of file path and characters. And this one's IO of list of file path and characters. So there's something we wrote already. Where was that? It was in list. Maybe we didn't write it. I'm not sure we did write it. Okay. Now I'm thinking, how is this meant to be done? Got a list of file path. I mean, I know how to do it. I just don't know. Given what we know, I guess. Hang on, is there another? So I don't see traverse, but is there a sequence? Oh yeah, here we go. In applicative, there was a sequence thing that we implemented. There we go. That's what we implemented. That's what I'm looking for. I know we implemented something like this. So notice how this lines up with what we've got. We've got a list of file paths. Well, kind of. We've got this list of... Let's go ahead and do this. Hey, thanks for the follow. Oh, got a raid going on. How's it going, everyone? Oh, thank you, higher order function. Thanks for the follow. You got a good name. I'm just going through something called the Data61 FP course. The Data61 FP course is something that our like a Commonwealth research organization down here in Australia. We Data61 goes around Australia showing people how to write functional programs, and they've come up with this FP course, which is just like a workshop that they teach. They usually do it only in 3 days, and so. Actually, I think I've probably only done this for 3 streams, so I think we're about on track to. Maybe we're a little bit behind, but we only spent a couple hours on it so far. But yeah, anyway, it's a workshop that they teach. It's really good. It's a really good workshop. It goes through how to basic types like list, functor. Oh, sorry. It goes through first of all list these data types. And then course.optional, and then goes through like list, functor, applicative, monad. We're up to FileIO, that's what we're implementing. I'm just trying to remember what the best way to implement this one is. I feel like I've gotten something a little bit weird somewhere around here. I don't think this is right. Given a file name, read it. There we go, yeah, I missed that part. So I did miss that part. Okay. I'm gonna back up slightly now. I'm gonna redo run. Because I know I got that one wrong. Because we are meant to do read file. I'm meant to use this one first. So read file. We're meant to read in the file. This makes more sense to me. So we're meant to read in this file, FP, which is our file path, and then we're meant to do something with it. So we've got our characters now. There we go. Oh, you've heard of me. Awesome. How's it going? How have you heard of me? Have you heard good things or awful things? So this is going to be our content. Thanks for the raid. Okay, content something. So we've got this content in scope. So then it says read it, and for each line in that file, read and print the contents. So for each line, oh, we have this lines function, don't we? We have lines here, lines, which takes our characters that we've got, our content. So if we say, oh cool, you've seen the strange loop talk, awesome. So we've got our list of characters, so now we can pass that in to our get files. Get files, those lines, and what did we have before? We had print files, I think it was. Print files, was it? I think so. Oh, that's right, we dropped this. There we go. Alright, so we're back on track. Now we need to implement get files. So now this is a list of file path. Right, and we had this, what we got up to was sequence. We have this sequence function that I know that we've written before. So sequence takes a list of something. So if we've got these list of file paths, but this f of a, and what we want back is an f of list of a. So what we could do is a get file. Yeah, if we give it, let's put in a hole here. So I think we need to use sequence. Just because list of something, get back something of a list. And that kind of lines up with what we need. If we have a list of something, we need to get back something of a list. So if we put in sequence there, what do I need to give it? A list of IO file path and characters. And what I have is a list of file path. So what if I use get file? I know I need to use get file as well. So what if I get file on each one of those, on my X's? There we go. So that lines up, type checks at least. Yeah, I'm the guy with the parrot. It's my brother's parrot. Okay, so a sequence, yep, that looks good to me. So for each one of these, for each one of the files that we get in as an input, get the file, and then we use the sequence thing to kind of flip it around, so then we get back an IO of list. So that takes we had a list of what we had before we run the sequence function is a list of IO, and then we run sequence, and it flips it into that. So now we've got an IO of list. So that makes everything line up, and type check. Cool, so we're almost done. We need 3 more functions. 3 more functions and our program's almost done. So we have to implement get file now. Okay, so we need to use, so we've got a file path, fp file path, and I know read file. Read file will give us back our IO of characters. So what we need to do is go from IO of characters. So let me show let me put a hole in. So I'm just making a local binding X. So I need to give back an IO of that, and I have, so X is an IO of characters. So see how this is, I need to give an IO of file path and characters. So this is a tuple up here, and I have an IO of characters. So I need to convert this thing into that thing. And so this file path, I'm guessing, is the file path that we passed in. So I'm going to use Fmap. And so this is our characters, right? So put another hole in here. So I'm going to use Fmap. And I have to give it a tuple of file path and characters. And I have characters. So I've got the second part of the tuple. I also have the first part because that's just FP. So there we go. So now I've implemented get file. So that was just, using types to kind of direct us toward a solution there. 2 more functions, print files and print file. Okay, so I'm guessing, so we've got this list of file path and characters. So I'm going to, for each one I'm going to print out the file, right? So fmap, so print file, fmap, our files, so let's introduce that. Oh, actually we have, so this is our tuple actually, isn't it? So let's do this. So we've got 2 holes. One we have to return a b. That's not quite good because b is a type variable, so it could be anything. What can we do? So we're going to do the same thing as what we did before where we had a sequence, right? Because for sequence, we noticed that up here, what sequence did was we did fmap and then we did sequence, and that means like for each one of x's, do this thing. I'm going to do that again, so sequence, and I'm going to do fmap. So for each one of the x's, I'm going to print it out. So I'm going to put print file in here. This won't type check, this is wrong. So that's not going to type check. And neither is this either, because sequence is going to, so this is an IO of units. This is going to give us a list of units, and that's not what we want. So I'm going to put in void as well. I know that I'm going to use void. Remember, void is, I don't know if, yeah, so void f of something, so this is going to be our IO of list of unit, and then it's going to give us a list of just a IO of unit. So it's just going to make the type line up. So that's why I'm putting void in there. Sequence is going to give us a list, an IO of list of something. So this is print file. I'm going to put in a hole back in here, just to, there we go. So now I need to write a function that goes from tuple to IO. And so I want to use print file as this thing here. So what I have though is a tuple. So I'm going to tuple print file, and then I need to give it a file path and content. So I need to give it, I've got the two holes, file path and content. There's my two holes, and what I have here is file path, and what I have here is the content. So I need to extract it out from the tuple. If you look at the top, it says there's a couple of useful functions for tuples, first and second. First of the tuple and the second of the tuple. This could actually be rewritten. There's actually a built-in function that does that sort of thing. The tupling and it removes the tuples. You just have to do what's it called? Uncurry. So that's equivalent. You don't have to understand that at the moment, but that's equivalent. Okay, so that should type check. Yep, we've got one more function, which is to print the file. And it says use put str line. Oh, and the output looks meant to look like this, isn't it? It's meant to look like this thing. So we need to put str line of that. And plus plus, remember, is concatenation. So we need to print out the file path and the content. So bind, ignore the unit, because if you look at the type of put strline, gives back an IO of unit. Unit has only one value, so we don't really care about it. And then it needs to print out the content. So that'll print out the header, and that'll print out the content. So if we reload this, that should be the program done. Yep. Main. There you go, that looks exactly the same as this. You can see that these are the same things. So we've implemented this function, this program, and all we've done is used functions. So this module is to demonstrate that we can do FileIO, so IO with files in that, so we can write a practical program, and we don't even need to write side effects, we can just write pure functions. I'm going to clean this up a little bit. I'm going to show you how to clean it up a little bit. So here we actually have syntax in Haskell for this. So instead of using that bind, we can use this do notation. This is called do notation. And so when you use do notation, it just means that these things are equivalent. So you can get rid of the bind and just write lines instead. I'm going to do that up here as well. So up here I think we had something that, yeah, here we go. So I'm going to replace this with do notation, and that reads like this instead. So that's the same. So it's just kind of a way of kind of flattening it out. Is there an advantage to using do? Do just syntactically is a little bit, so you can see here it gets nested. Do just removes the nesting. That's all it is. That's really the only advantage, that you're just removing the visual, like the syntactic nesting in your program. It doesn't actually, like, semantically it makes no difference at all. If you want to write your program in terms of do always, that's fine. It makes no difference. It's just syntactically, it just looks a bit different. Some people find this a bit easier to read. If it makes no difference to you, then it doesn't matter. No real advantage other than people find it more readable, and it removes this nesting. It's purely syntactic. So I can do this here as well. There we go, and here I will actually replace this with uncurry. So that's all just refactoring, and if it type checks after my refactorings, I'm usually pretty confident that I've done the right thing. So there we go. I mean, this looks pretty good to me. There is one more thing I'd probably do. There's something, instead of sequence, when I see a sequence and Fmap together, there's actually something called Traverse, which does the same thing. But I don't think we've actually written that in the FP course at the moment, so I don't think this will work. We'll give it a go. Yeah, variable not in scope. So that doesn't exist yet, but there is something called Traverse, which reduces the duplication there. And then when you see void and Traverse, Haskell's built-in thing has got a Traverse underscore. So really, ideally, this could be written as. Ideally, it'll be written as that, but we don't have any of those in scope, so we're just gonna leave it as sequence and void. It's fine. It's just code duplication, and there's just those things already exist in the standard library. Okay, so that's pretty good. I think that is good enough for FileIO. What's the next one? State. Will you go to state? We can go state. Sure. Actually, I haven't done any of these ones before. I've never taught these ones, so I haven't done those. What I have done is the Traversable one. There's a couple of problems with Traversable, but we could do that one. And people really like the parsers one. So I don't know. The way that I've been doing it at work is I've been skipping these ones. These ones are alright, but I've been skipping them. I haven't really done them before. I've just been skipping them because people have been asking for Traversable. They're a bit confused about Traversable. And I've been trying to aim for the parser ones because people have a lot of good feedback about doing the parser ones. So I don't know if I should go through state, co-monad, compose, or if I should just go straight to Traversable. I'm not sure if I should do that on stream or not. I haven't done state before, so I don't know what's really involved in that. Might go Traversable. We can always come back to state. Yeah, actually, so compose. The correct order is actually compose and Traversable. So we'll skip these ones for now. We can come back to them if people request them. I'll come back to them. But I'm gonna go to compose and Traversable, and then I'm gonna skip list zipper. I don't really care about that, and then we'll go to parser. So I think what we'll do is skip these ones for now. Skip list zipper, and we'll just go compose, Traversable, and then the parser ones. And then I'm not sure about these ones. I don't know if we should go to those ones or not. Okay, cool. So let's go compose. This is compose is really good. Compose is a really good exercise. Okay, so we're creating data type called compose, and it takes two type constructors, f and g, and then it takes a type a. So if you look at the kind, remember our kinds from before. Kind of compose is type constructor, type, and then it makes a type. So this could be like list. So you know how like list takes another type. So list, you got a list of ints. You don't have a list, you have a list of ints. So this could be a compose of list, and optional is another one. So optional of int, optional of string, optional boolean. They're all things. So this could be a compose. You can actually make a compose of list, optional. Whoops. There is optional, right? Oh, yeah, I made a typo. So compose, list, optional, and then it takes a type, so I could say int. There we go. So that's an example of using the type compose. So you give it two type constructors and a type, and you get back a type. And what it does is it just wraps it up. So f, g of a. So if this was list and that was optional, this would be an optional of int, and then a list of them. So a list of optionals. That's what compose optional or list optional a would represent. A list of optionals. So it's just a way of putting two type constructors together around a value. And when we write this type, we can possibly implement some instances. And so it says up here, exactly one of these exercises will not be possible to achieve. Determine which one. So we have to implement 3 instances here. So we've got functor, applicative, and monad. So one of these is not going to be possible. Does anyone want to take a bet which one's not going to be possible? One of them is not going to be possible. Functor, applicative, or monad. One of them is not going to be possible. Okay. You're going to guess that monad's not possible. Why would you guess that? There might be a reason for why monad's not possible. Why would you guess it? I'm going to start implementing it. So, actually, so what's I forgot to. You think you've heard that before? You think you've heard that monad there's no monad for compose? Monads do not easily compose. Okay, cool. We'll see what we can do. So let's try and implement functor. So we've got this type. I'm going to copy and paste this back into the file. Monad is a superclass of applicative superclass of functor. Right. Well, I'd say the other way around. Applicative is a superclass of monad, and functor is a superclass of applicative. But yes, that's exactly it. Yeah. So because all monads have to be applicatives and all applicatives have to be functors, and only one's going to be one of them's not possible, then that means that it must be monad, right? Because if we can implement 2 of them, we have to implement a functor and applicative to implement monad. So if we can implement at least 2 of them, then we know that the only one that is not possible is monad. That's it. So just copy and paste that back in. Hopefully that. Oh, I have to enable instance sigs. Exactly. By deduction, has to be monad. That's not possible. Okay, so I've just copy and pasted the signature back into this file. So we've got a F, we've got a compose FGA. So we have this in scope FGA. We've got an A to B, and we have to implement a compose FGB. So I'm going to put in compose here. So we have to construct and compose, and so now what we have is we have to give it an FGB, we have an FGA, and an A to B. And what we know is that there is functor in scope. So what we've said is that F is a functor and G is a functor. So when both of these are functors, then we can implement functor for compose. So what we can do here is if we know that F is a functor, then we can use Fmap in here. So now we have to go to function g of a to g of b, and we have this a and b in scope. And what does that look like? That looks like fmap. So we can say f. So fmap over our g with f, and here what we're saying is run that fmap over our f. So this removes the f from our. When we have fmap on our FGA, we get a function that goes from g of a to g of b, then we run our fmap on our g of a to g of b with our f. So that's just composition of fmap. So we just use fmap. Fmap twice, one on the f and one on the g, and that's how we implement fmap for compose. So that one's possible. So now we have to implement applicative then. What would pure look like? Pure A. So we need to implement a compose FGA. Well, constructor compose, let's use that. So now we need to write an FGA, and we have an A. Well, we can make a F using pure. then we have to give it a g of a. Well, we can make a g with pure. Then we have to give it an a. So a. And we can actually remove that. So we go. So for the pure, it's just pure composed with pure, and then with the we just construct we just use the constructor around it. So the compose instance for applicative of f and g is just the composition of pure. That one's easy. So let's put that in there. So the whole says that we have to implement this. I'm going to copy and paste that back over. Okay, so I need to implement this. So if we have a compose with a function inside of it, then we can go from compose FGA to compose FGB. So let's, so this is the compose FGAB. FGA. Whoops, that's not right. Compose FGA. There we go. So what do we have? We have this, and we have this. So we have a type constructor, another type constructor around a function, and then we have a type constructor around a value that we can pass into this function. And then we need to get back a compose. So let's use the compose constructor in here. So now we have to give back an FGB instead. So FGA, and then this thing here, and then FGB. Alright, what can we do on applicatives? Well, we can use this apply. So I'm going to put that there in FGA. So we know that to implement what we've seen so far, right? We've used Fmap to implement Fmap for compose. We've used pure to implement pure of compose, and similarly, I think we're going to have to use apply to implement the apply for compose. So what I've done in here is put in this this thing here. Put in apply to say apply FGA to something. What do we need? We need to give it a f of g of a to g of b. And we've got this thing. So we should be able to, in here, what if we mapped out FGAB? So we've got this FGAB, right? So what if we kind of map this? We want to change this thing, right? We want to change this. So if we don't really care about the F part, that's fine. That can stay. The F part can stay, but we need to change this part. So I'm going to put in another hole in here, and I'm going to just Fmap this. So now I put the hole in here. So this is what I have to fill in, right? I have to fill in a function that does this. Takes a g of a to b, a g of a to a g of b. What does this look like? And that is our apply. Let's apply but on our g instead. So if we do that, that lines up. But what's interesting is I'm looking at this and I noticed that it looks the same as something that we've already implemented before. Come on. So look at this type. Notice the implementation there and the implementation of this thing. So notice how we do Fmap and then we do apply. Here we do Fmap and then we do apply. Looks exactly the same. So what if we just reuse the function that we've already written? There we go. Same thing. Cool. So we have implemented compose for, we've implemented the applicative compose, we've implemented function compose. The only one left is monad, and remember at the top it said exactly one of these is not possible. It must be monad. And it must have been also because monad implies applicative, which implies function. So if there was only one that couldn't be done, it was monad. So I'm going to actually try and do this, and I'm going to try and show where this breaks down. I'm going to try and show why we can't implement this type. Why monads don't compose. In English, this means that monads don't compose. And in English, this means applicatives compose and functors compose. Functors compose, applicatives compose, monads do not compose. I'm going to try and show why they don't. So we need to implement this, a value of this type. We have to implement bind given this type. So we've got this f, and we've got a compose fga. We need to give back a, well, we can leave that off maybe. Okay, so we've got this thing that goes from A to compose FGB, and we have this thing. So we need to have, the only way we can get an A is from this thing, right? FGA is the only place we can get an A from. So we've got A to compose FGB. The only place we can get an A from is there. So how can we get access to this? Well, we can map it. That's one way to do it. Let's have a go at that. We'll map it. FGA. What's a good way to do this? Do this anyway. Alright. Let's go with this. Okay, so we've got this, what we have in scope is f of b, is that right? Right, okay, cool, yep, ignore that. Cool, okay, so we've got g of a to b. So I've got this g of a in scope now. So what I could do is write another thing, so I've got this g of a, so now I could write g of a, could fmap that. Okay, so now I've got access to the a. So I've got an a and I can return a b1, so b1 is whatever I come up with. I can come up with whatever I want, and I can return whatever I want. Now I've got this function f of a to compose fgb, so I'm going to use that. I'm going to say this is f. So now I reload, and it tells me that what I've just written, so fmap of fga, fmap on ga, and then given an f, what I have now is an f of g of compose fgb. So I've got fg, and then if you unwrap this, you'd have an fg fgb. So it'd look like f of g of f of g of b. And so in our monad, remember how we had I think it was called join? Yep. We had in our join function f of a to f of a. We kind of want that, but we can't really do it because we've got this g. Like, if we could kind of collapse both of them together, that'd be good. But we can't do that. And so how can we kind of lift? We just want to get rid of like the duplication. And really, that's where you get stuck. You cannot get rid of this duplication. There's just nothing that we can use to get rid of this duplication. And in the end, what that means is that just monads don't compose. There's just no way to, once you kind of get into once you kind of get access to the A, you kind of got no way of unwrapping things. And so if you can get access to the A, but then you can't do anything with the result of that to be able to collapse these together. And so what you end up with is just kind of like a nested thing, and that's why you can't implement compose. You just can't. You get in a nested situation where you just you map through one of them, but then you've got something hanging around on the outside. So it's impossible. There's no way to do that. So I'm just going to delete that code. There's no way to implement a monad for compose. Good example of concrete F and G that makes it obvious why it's not possible. No. Well, there probably is a good example of concrete F and Gs, but a lot of F and Gs that you come up with, you can do it for. Like if I if I tried to implement this gives rise to something called monad transformers, right? So because monads don't compose, what can we do about that? Well, what we can do is implement. This is not going to be quite valid Haskell, but we'll go with it. So if I can't choose, so if I can't say for all F and all G, I could say list and optional. What could I implement compose for this? And the answer is yes. I can actually implement a monad for this. I can actually implement a compose list optional monad. So if you're asking for concrete F and Gs, there's actually a lot of them where you can implement it. You just can't do it in general. You can't, like, the list and optional list, a lot of pretty much all the common ones you can think of, like list and functions, all of the common monads that we've implemented so far, we can implement this type. So list, optional, list, optional. Now this is really dodgy Haskell. You don't want to ever write this, but yeah, I can't even do it. But the idea is that you could actually implement this. You could actually implement this function, and you can actually be specific for kind of this part. If you can, the part that we got stuck is that we had this G in the way, right? When we had before we had f of G of f of G of A. Now what if you could get rid of this G? If you get rid of this G, you'd end up with that. And then you could flatten it and you'd be set. But because we've got this G in the way, we can't do it. Now, if we said optional is the G, so I could actually say F here, generalize it F. And what we're doing right now is reinventing monad transformers. That's exactly what you've done, reinvented monad transformers. So I can say, instead of having a compose type, I could say this is an optional T type. And what that represents, an optional T, so instead of this compose type, if we said optional T, right? We could say we can actually implement a monad for this optional T type. Let's have a go at that. I'm gonna import it. This is actually really good. Let's go through this. This is really good. Yeah, G doesn't work. Yeah, you can't say for all monads. You can't say G is a monad and therefore I can implement it. But you can say if I know G is optional, or if I know G is list, or if I know something about G, then I can implement it. And that's what we use. That's monad transformers. When we know things about G, that's what we call a monad transformer. And so here, what we've done is optional T is a monad transformer, and that's because we know what G is. So now we can transform. That. So let me go through. We'll actually write this one. This won't be good. We'll write. So it wraps another F, right? So this will be F. We'll call it FA. I don't know. If this will go. Yep, cool. No instance applicative. Oh, okay. So we need to write the applicative. Let's ignore that for now. Let's ignore the applicative. Okay, so found a hole to do, so we need to give it an optional T, F of B. So we know that F we can bind on. And now we've got a to optional T, F of B. So we've got this A. And you have an optional T f of b. Well, that's what we have to fill in. And what we have is that. Hang on, that doesn't make sense. To do optional T f of b. Oh, whoops, I've done the wrong FA. There we go. Here we go. Now we're getting in the right direction. Okay. So I have... Alright, I have to say... Monad F. Sorry, I'm coming up with... I'm actually writing code right now. I haven't come up with this exercise before. So let's... But this is pretty good. If G were IO... Yeah, exactly. IO is a good example, actually. That's a really good example. Because you have to run the IO. Exactly. You've exactly come up with the problem. You've exactly identified the problem. Yeah. So if G was IO, and that was IO. So we've got this F. We don't know what F is. Yeah, that's a good example. Yeah. So if we have F, so let's say this is a list. We've got a list of IO, a list of IO. Let's say we can compose a list in IO. IO has a monad, right? So yeah, this is a really good example. It's a list of IO, list of IO. So somehow we'd have to like, is this right? We'd have to run one of them anyway. I can't remember if the problem occurs when it's like this. I guess probably not. The problem must be when it's like that. But anyway, you'd have to kind of run one to be able to get access to the list and be able to identify, yeah, how many elements are in this list? How many elements are in this list? You don't know unless you run the IO. And then you're executing side effects. So you can't do it because IO is a monad. And so if you went to try and implement this specific one, you'd have some problems. Because the list of this, the length of this list depends on this list in here. So you can't really determine the length of this list, for example, until you know what this list is. So we can't write a transformer for IO. We can't write a monad transformer for IO. So it's just basically, when we write monad transformers, it's because we can't write them in general, so we're writing them for specific cases. So we can write it for optional, so that's what we'll do. We'll do it for optional. So we need to give back an F of optional B. What we have in scope is A2. We've got this function in scope, so F of A. I'm going to say run optional T, takes an optional T. I'm going to introduce this thing, optional T FA to F of optional A. Let's see if I wrote that right. Oh, there already is optional T. Whoops. I'm re-implementing something. I'm just telling it to ignore my optional stuff. Ignore the optional stuff that I'm writing down here. Of course, it already exists as an exercise. I probably should have just went there and started teaching there anyway. But we'll finish this off. Okay, so this passes. Okay, that passes. Okay, cool. So I should be able to say run optional T here, because it was expecting an F of optional B, and I was giving it an optional T. So that should work. Why is that not? If G is some sort of box type like maybe or either, you have to figure out what to do, but it's talking about some value that will only appear after some side effect. You can't get it without executing side effect, hence running into trouble. Yeah. I mean, there's more than just side effects. Is it like, there's more than just IO, which is a problem. There's a couple other things that are a problem as well, but you have to basically, yeah. You can't use just monad to be able to implement it. You have to know more about than just monad. You can't just use bind. But yeah, you run into problems where even if you know something about it, there's certain things you can't write data. You can't write a mono transformer for I/O. You can't write a mono transformer for quite a few things, but you can do it for optional. And I'm just struggling to do that right now. I'm really close. I'm struggling a little bit to finish as it should be. Yeah, that's right. So optional T. I'm not sure what the problem is there. Oh, right, we have an optional. Oh, of course. Okay, so A is not an optional. A is right. A is sorry. A is not an A. It's an optional of A. So we have to. We have to actually do something with that, which is we don't have the fold function, but what we can do is map. Map it, and then we can say get, otherwise get empty. So I'm using this pure here to pure it into the F. You don't have to understand too much about this. Just know that if I know something about option, yeah, there we go. Cool. So I actually implemented it. Cool. Ignore this error as well. We just didn't write the applicative. There is an applicative for it, but we didn't write it. But you don't even have to understand the implementation here. Just know that because I know something about optional, I can use these optional functions in here. So I can use this question mark, and I can use this map. So I know something about optional, therefore I can do something about it. So that is the motivation for mono transformers. There actually is an optional T in here as well somewhere. Optional T. Oh, it looks like that's in the state T. Oh, okay, maybe we should have done that. Maybe we should have done state T. But yeah, now you should know that why mono don't compose, and also what we can do about specific versions. So we can do something with optional because we know something about optional. We know something about list. Anything that we know enough about, we can implement this as long as it supports something that as long as it doesn't have to do things like side effects or something like that. So there's no such thing as like an I/O transformer, but there is something there is such thing as an optional transformer. So that's the motivation for mono transformers, and the motivation is monods don't compose. Cool. Okay, so that was a good detour. Maybe we should actually do state and state T, because it looks like there's actually optional in there. But anyway, the motivation I was trying to get to, traversable. So now that we've implemented all these instances for compose, there's actually another thing that we can come up with, which is traversable. And so if you looked before when I did my sequence, I did sequence under applicative, I think it was sequence. Yeah, sequence. So sequence, it kind of takes like an applicative and then a list of FA and then an F of, then it takes it to like a list, F of listing. So it kind of like flips the constructors around, the type constructors. And that's what this does, but more generally. Traverse takes a T of A's, where T is traversable, and T also has to be a functor as well. So functor is a superclass of traversable. And so if you give if T is traversable, then you got this function traverse, which takes a T of A and a function A to F of B, and then gives you an F of T of B. So it kind of takes this thing. So imagine if T was list, and you have a function that goes A to, I don't know, IO of string or something, then you get back an IO of a list of strings. So it kind of takes one type constructor and kind of runs a function over every element inside that type constructor, and then flips the constructors around. So if we implement traversable list, we're just going through and we are what you can think of traverse as, actually one really good intuition for traverse is that you're deconstructing the outer type constructor and you're reconstructing it inside of another type constructor. So here, remember fold right is deconstruction for a list, and you give it two things. You give it the cons and you give it the nil case. So fold right will replace cons with something and nil with something in a list. Remember that. Fold right for a list replaces cons with something, nil with something. And so fold right in traverse is we're replacing cons with cons, but that cons works within F. So we're replacing cons with cons but in F. And we're replacing nil with nil but in F. So traverse is being able to deconstruct the type and reconstruct it within another type constructor. That is what traverse means. So we're missing some stuff. I've implemented a couple more exercises in here. I don't know why they're not in here. I don't know if this is probably we're probably gonna get merge conflicts in here. I don't know. Yeah, we are. That's annoying. Can I check out just master's version? Traversable. There we go. Alright, so let's go back, hopefully. No problem, thanks for dropping by and thanks for the raid. I did add more stuff to Traversable, so I don't know why. Yeah, I did. I'm not sure why they're not showing up in here. Oh, here we go. Oh, somehow they're showing up. Is that it? No, that's applicative, isn't it? Oh no, this is traversable. Okay, cool. Somehow I've got them now. Okay, whatever. Alright. So so we did traversable for list, we already talked about that one. So now we're going to implement traversable for exactly one. So we've got our function, and we've got our exactly one of A. Now we have to implement f of exactly 1b, and what we have in scope is exactly 1a. In A to F of B. So remember that it is deconstructing and then reconstructing. So EOA, if we are run exactly one, that is the deconstructing part, and then we have to reconstruct it in F, which is just mapping it with exactly one. So this will, if you look at this is deconstructing, then we run our function over it, so that will give us an F of B, and then we have to reconstruct it inside of our F. So that is traverse for exactly one. So we've got the deconstruction part here and the reconstruction up here. Let's do that with optional. F, optional of A. Okay, so I think yeah, I think a good place to stop is when we actually we'll derive this this sequence A, and then I think we'll get back to work after that. Okay, so we'll implement this, so traversable optional. Let's look at this. So we need to return back an F of optional B. What we have is optional A and A to F of B. What can we do? Well, we can, what's a good way to do this? So we've got our optional A, we can map it with F. And what that gives us is, what's a good way to say that? So now we've got an optional of F of B. Oh, we have to deconstruct though, don't we? We haven't done the deconstruction, so whoops. I guess that is deconstruction. Yeah, it is. In some way, because we're doing a map. Okay, let's go back. So we've got an optional of f of b, and we need to get an f of optional b. So what we can do is yeah, this kind of sucks. There's a better I'm gonna write a function. There is a function that makes this really straightforward. Just makes it obvious what we're doing. So I'm gonna write the fold function for optional. So a to b. So this is the same as fold right. So optional, this optional function is going to be like fold right is to list is what this optional function is to optional. Which is that if you think of optional as either as a list that has maximum element one element, or you think about the constructor replacement. That's the important thing. So I'm going to implement this function. We need to give back an optional a. Oh, whoops, yeah, optional a to b. So we've got this b. We need to give back. So we've got this b here, so we can give back that. But then we've got this thing here. So optional a, we're going to map it. Whoops. Going to map our optional a, and then we're going to say, or otherwise, give back b. It should be the same. No, it's not working. There we go. That was the problem. Just need to put parentheses in the right place. Okay. So this type is just saying replace the. It doesn't look obvious in the implementation, but you can read it as this. It's replacing. If you give it a full, that's the replacement for full. This is the replacement for empty. And fold right has instead of full and empty, it has cons and nil. So this is just a more simple version of fold right, but it's for optional. So now implementing this is really simple. It makes it really simple because really remember, if you remember traverse, we just use our fold right because we deconstruct and then we reconstruct. So this will be exactly the same. So we're going to reconstruct empty, but inside of our f. So we just use pure empty. And we need to reconstruct full, but inside of our f. So we can run our f, we've got its a, so we can run f of a, but then we need to reconstruct it into full, so we just map over it. And that's the same. So that makes it really obvious. Deconstruction and then reconstruction. So deconstruction of, so when you use optional and you use this optional type, this optional function, what we're doing is giving it what to replace full with, giving it what to replace empty with. When we reconstruct, all we're doing it is using f, using like our applicative, rebuilding it inside that applicative. Okay, so I'm gonna implement this one function, then I'm gonna finish up there. We'll do these ones next time. We're gonna look at the composition of traversables, and then we're gonna look at these other types as well, like product and coproduct. That'll be what we're doing next time. Okay, so sequence A. So remember how in applicative we had this sequence which works over list, and notice how this is the same, but instead of list we have T. So this is just a more general version of sequence, just a really general version of sequence. So we've got this TF of A, load it up over here. Need to give back an FTA, and what we have is the TFA in scope. And what we also know about this is that it's that we have traversable. T is traversable, so the only thing we can really know to do is to use traverse on our TFA. Hey, thanks for the follow, King. Okay, so if we use traverse on our TFA, then I mean that's the only thing we can really do. Oh, also thanks for the follow. Yeah, all we know about TFA is that we know it's traversable. That's pretty much all we know. So we know pretty much what we can do is traverse on it. That's what we know. So if we call traverse, put in a hole. if you want to understand what I'm doing, should I watch your YouTube videos? Yeah, I've got a couple of YouTube videos up of me starting it up. I did. There's a part 1 that I did. But really quickly, what I'm working on is this Data61 FP course. Data61 is a Commonwealth-funded research organization down here in Australia, and they make this functional programming course, which is a course that they use to teach people functional programming, and they do it as a workshop. They do about, I think 3 days is usually what they use to go over most of the things in this. But the workshop just goes through simple things like data types, and then it builds up a little bit and goes to functor, applicative, monad, FileIO, and then it just keeps building up. So it's just a way of teaching Haskell. It's just a Haskell course. More generally, it's a functional programming course, but they just use Haskell as like a tool to teach, because Haskell is a really good tool to teach functional programming. So what I've done so far, what I've been doing is I went through I did optional, list, functor, applicative, monad, FileIO I did today, and then we went through compose, and now I'm currently going through Traversable. So if you want to look at part 1 was, I think, optional and list, and maybe functor. No, I think it was just optional and list. I think part 2 was functor, applicative, and part 3 has been monad, which is today, monad, FileIO, and compose. Currently going through Traversable. I'm going to end it in a few minutes, but look through part 1 and part 2, and you'll be able to see these first ones. Cool. So traverse is the only thing we can do on this TFA. Just based on, like, we know nothing about T other than it's traversable. So the only thing we can really do is call traverse on it. Yeah, I'm going to upload part 3 on YouTube as well. Yeah, you'll be able to watch it on YouTube. So the only thing we can do is traverse, put in a hole says F of A to F of A. What does that look like? A to A. That compiles. That's the same as ID. And also I can delete that and that. There we go. So sequence is just traversing with the identity function. That's pretty cool. Yes, that looks like me. Okay, so I'm going to end it there. Sorry to the people that have just come in, but I've been going for a couple hours now. So I'm going to end it there. What I am, I'm going to commit this, and I'll upload the video to YouTube. And then next time what we'll go through is showing that traversables compose, and then we'll come up with these new types, product and coproduct, and we'll talk about what those mean and what you can do with traversable with those. No problem. Thanks for coming in, and thanks for watching. Feel free to ask more questions. I'm always happy to get interrupted and go on a weird tangent about anything. I'm always happy to. I mean, the whole point of this is that I'm just trying to show some Haskell, trying to get people interested in it, trying to get people to learn it as well. So if you've got any questions, I'm really happy to go through any questions at all. Okay, so let me find someone to host. Always like hosting someone else when I leave. Also, I started up a functional programming. Is it a community? I think I started up a functional programming community. So you can subscribe. I think you can subscribe to that or follow it or something, but I don't think it's very useful. I don't think it actually tells you very much, but it's a good way to group people, I think. Okay, Evening Rust. That's the closest one so far. Cool, thanks for that follow. Oh, here we go. Fred is doing something, so we'll go there. He doesn't speak. I don't think he speaks much English. But he does write Haskell, so I think we'll go there. Or maybe he does does speak English, but he just doesn't. Maybe prefers not to. But anyway, that's where we're going. Okay, cool. So say hi to Fred. I am going to have to do some work now. So say hi to Fred. I'll upload this to YouTube. I'll commit what I've got so far. Push that up onto GitHub, and you should be able to see links on my Twitch page to be able to see what I don't know, to find out any resources. So cool. I'll see you guys next week. I'll keep going on with the keep going on with Traversable. So far we got to sequence A. I'm going to keep going on with Traversable and finish off that. And then if you've got any requests, if you look at the FP course and you've got any requests in the README, if you've got any specific modules you want me to cover, I'm happy to cover any of them. Current plan is to go Traversable and probably go on to parser ones. So go on to that one next time. Cool. All right, I'm gonna host Fred. I'll see you guys next week, and check out my YouTube. Cool. I will do parser. I'll get to parser. Parser looks good. I will get to parser. Cool. I'll see you next time.